Okay, hello. Welcome to my channel. Today we're going to talk about the photoelectric effect. And the definition of photoelectric effect is that when you shine a light onto a piece of polished metal, it's gonna emit electrons. And those are called photoelectrons, hence the name photoelectric effect. And this effect has three properties. First of all, is that the frequency of the initial light beam have to be greater than the threshold frequency for it to produce electrons. Uh, and the second one is that the intensity of the photoelectric current is proportional to the intensity of the light. And the final property is that the energy of the photoelectron is independent of the intensity of the light. And the energy of photoelectron will increase linearly with the frequency of light. So what this means is that the amount of photoelectron emitted will change when the color of the light changes and not the brightness of the light. And we're gonna talk a little bit about history here. So the photoelectric effect was first discovered in 1887 by Heinrich Hertz. He accidentally done this by shining UV light onto metal electrodes and found that they require less voltage to produce spark. And this was later worked on by Philip Lenard in 1902, and then to 1905, Albert Einstein proposed the complete photoelectric effect, and that earned him a physics Nobel Prize, I believe. And Einstein established that light is composed of discrete packets of energy called quanta, and this was later renamed to a photon. And he has an equation here, the Planck equation from Einstein 1905. So he said that light is composed of discrete packet of energy he called quanta, photon, with the energy is equal to hf, and this is the Planck equation. H here is a constant and f is the frequency. And to see this a little bit like clearer, we're gonna talk about the energy of the photoelectron. So the energy of the photoelectron is equal to E here minus W. So what is W? Now you have to imagine, example, like a molecule with like different Bohr radius here. And suppose your initial electron is here, it's your E minus, and you want it to emit a photoelectron. And to do this, you have to shine a light onto it. So this is your light. You have to like, initially just like this. Want it to take this up here to this. And this thing is called W. So W is the energy needed to release the electron for it to emit a photocurrent. So this is the equation you use to calculate the energy needed. So we're going to talk a bit about H bar now. So well, H bar is a very special number, we can say. It is called the Planck constant, and it has the unit. This is for the unit of H bar is equal to mass times length squared divided by time. Length squared divided by time. Sorry. And from this one, we can like get something called the Compton wavelength, which is lambda equal to h divided by MEC. This is the Compton wavelength. It is the wavelength of a photon with energy equals to the rest mass of a particle. A lot of words there, I know. So well, that is probably it for H bar. I mean H. Now we're gonna move on to the Einstein equation of this m squared c to the fourth plus m squared p squared. So this you've probably seen in relativity. This is the full Einstein equation, and from this we can derive some equation for a photon with mass 0. Let's say a photon with mass equal to 0. We get the energy. The energy is equal to P times C. Oh shit, I did it wrong here. It's C squared. So the energy of the photon with mass 0 is P times C. And P is equal to the energy. Yeah, from this you can derive P equal to E over C. This is equal to HF over C. And this is H over lambda. Lambda is the wavelength of the photon. So I think this will be it for today. Next time we're gonna talk a bit about Compton scattering and some demonstration. Then we're gonna talk about the de Broglie proposal, probably. Yep. So that's it for today. Goodbye.